next talk is about what I call the Simployee model, which is sort of the amalgamation of some work I've been doing over the last couple of years. Turn the sound down. The sound down. Okay, this talk is about the Simployee model, which is the amalgamation of a couple of years of work that I've been doing on automation. Working at a company that does custom printing and framing to sort of automate their entire order handling process from the time the order comes in from the client on the website all the way through the time it's printing and getting out the door. So the talk is the Simployee model, or everything I know about automation I learned from muskets and mustangs. Now, when we start talking about automation, there are kind of levels of automation. There's the ones that we all do really, really often, which are tasks. This is the really simple stuff that you do on your system, and then there's tools and systems. And the complexity of these kind of ramps up. Tasks are static things. This is usually the stuff you write where it's, I've got a series of 20 commands that I type 45 times a day. Let's write a shell script. The parameters tend to be real simple. They're a date, folder, a user, do this task of this. Usually don't have a whole lot of variation. They don't think much, they don't do a lot of work. These are file cleanup scripts, cache clearing, archiving and backup stuff, simple reports. Most of your cron jobs kind of fall into this category. This is your basic maintenance stuff. Then you get into your tools. Your tools are dynamic things. You tend to actually have some logic. They think a little bit. They do some conceptual stuff. They're still got real simple parameters. But the action, the output can vary based on what you give it, the state it actually starts to think. It starts to alter its outputs. Your examples here, server deployment scripts. They do different things based on parameters you give them. They might behave in certain ways. Batch processing things, reports that require some kind of interpretation rather than just spitting that data out of the database. Monitors for systems, that kind of stuff. Now, system automation is kind of what this talk is about, but the principles do scale down into tool automation reasonably well. They're dynamic, they're logic-based. They tend to combine multiple smaller tool sets into one piece, and they tend to support complex data structures. You can give them an XML file, all the information about an order, and it'll pick it up and start doing stuff. They tend to run persistently. They sit there and they wait for some kind of data to come to them. They're usually not just run by you. Web services, things like that fall into this category. Some examples: order processing, payment processing, customization tools, ERP and MRP integration to bigger systems. So, does anybody know who this guy is? Anybody? Very good, Henry Ford. And the slide that's actually missing from my presentation right now is Eli Whitney, which is the other half of this. Eli Whitney was the gentleman who didn't invent, but greatly advocated, improved the techniques for interchangeable parts in the 1800s, which kind of led your way into Henry Ford developing the automated assembly line. So the assembly line, or we're not building master craftsmen. One of the things that I've noticed tend to be a problem, this was the problem in the system that I came in to work on at my last job, was it was really, really smart. It was really complicated, it had a lot of things going on inside it. It could do a lot of stuff, but it was really complicated, really hard to find what you wanted to work on, really hard to alter, really rigid. Basically, the Simployee model uses agents, which are little tiny programs or pieces of programs. And they fall into more or less three categories. So you've got the Simployee, the manager, and the expert. Simployees are, by their very design, stupid, ignorant, low skill, low cost, and expendable. You build them that way so that if you need to replace one, if you need to change its job, if you need to train it to do something else, it's really easy to do that. Because they don't know a lot, they don't have to be aware of how to build the entire system. And car thing, the guy who screws on the headlights does not even know how the hardware works. That's unnecessary information. You don't need to train them for that. As a
When you say the assembly line worker and BMW is stupid, ignorant, those. I just imagine if this was public.
well, it's the it's what assembly lines are intended to be.
Exactly.
All right, now managers, they're the coordinators. They usually don't do any actual work, and the same thing applies. Not to disparage people who are managers, but they don't. They coordinate groups of employees. They monitor the system. They keep track of things. They handle interactions between various systems a lot of times. They assign the work. They regulate the workflow. In sort of more advanced systems, you can start actually building lines dynamically. They'll handle all of that work. Now, your experts. This is where you get into your data structures. If all of the employees have to be stupid and the managers don't really need to know what's going on, they just need to know their part. There has to be some kind of interface between the data structure that you're using to guide and control the system and the actual system itself. So when you build your experts, what they essentially are is the data handlers. They're mostly getters, interpreters. That way, employees can say, hey, what's this setting? And it says, oh, that setting is this. Use this, do that. They provide a lot of the information that all the agents need in a way that doesn't require the agent to actually understand the logic of your data structure. This is the part you're going to spend most of your time on. It has to be really well architected, or you're going to get yourself into reasonable amounts of trouble. But because it is all in one place, you can very, very quickly change the logic of any step of this. You need to alter the way things work. And these guys definitely don't do anything. They're there to simply translate information back and forth. So automation tends to work as a lane. And these guys, a lot of times, will be one script with multiple sort of methods and stages within them. There's the logic, fetching of the resources, the actual performance of the action. I recommend always having some kind of validation on the end of every line to make sure that things did actually do what they were meant to do. And that all of these stages can consult the expert whenever they need to actually know something to do their job. Now, one of the beauties of setting it up this way is you can actually parallelize any step in this process. We ran into the problem where downloading required a lot of our system resources, a lot of time. Image processing, running it through Photoshop, what we used, also takes a tremendous amount of system resources and time. So by splitting it up, we could have some things go through a single line, and we had 4 or 5 computers sitting there running Photoshop, processing 10,000 images every day. It allows you to really streamline things and keep things running short and clean by having some system that splits it out. And we use the ZimQ message queue system, which is great. If you guys haven't had a chance to look at it or use it, it's pretty cool. So when you build an entire project, each one of the lines handles basically one step of the process. And the main process will initiate and it will pass through each line in the system. Each line error out or pass it on to the next system. If there's an error, it passes it back and says, there's no good here. If it comes back great, awesome, everything. But this makes it really easy to add a step, to modify a step, If one product or one project or one process needs to go through a different series of steps, it's very easy to build a pattern based on it. You can also, individual lines can be modified. So based on the input, you can actually build and perform a different assembly line through the process. So it's travel. Or how to avoid becoming your own warden. This is something that when you get into automation systems, you really start to cause yourself problems very, very quickly, a lot of the time. It's really easy to design for what you're doing today and leave it at that. When you're architecting something along these lines, what you really need to do is consider the long-term goals, the long-term capabilities. Same thing goes with sort of using an idealized system like this, where your actual needs on any given system will not necessarily perfectly conform to any model that happens to live there. You have to kind of temper that against your actual use, where you're likely to experience change and such. But things to do to just avoid the major pitfalls is always consider the 10x and the 100x scenario. What is this thing going to do under load? If I multiply what it's designed to do by 10 times or 100 times, how is it going to handle it? Now, don't program for that eventuality, but at least keep it in your mind so that you know down the road, if this ever grows, you have an inkling of how you would go about doing that, and you'll naturally leave yourself in points to be able to expand the system that way. Keep all your boundaries clear. Don't set up systems that have to be in sequence, that have to, this must precede this every single time, or as soon as you get the exception, you're going to start having problems and it's going to become a nightmare of work to try to overcome that. Plan for change, but don't write the changes. Basically, it's really easy when you're working on something like this to say, oh, at some point in the future, I know I'm going to need to do X, so I better write that as a functionality. You don't have to write that as a functionality right now. It's not a requirement right now. But be aware that those changes are probably going to come. That will, again, stop you from blocking yourself off from those avenues and requiring major refactoring to go back and extend the system. And finally, when you get into that validation step I talked about, trying not to use the exact same logic that you did to determine it the first time. You should always use some kind of logic that works backwards from the output to compare, and then compares it back to the original. So, whenever possible, you don't want to say, run this function with these parameters, and then run that same function with those parameters and make sure that they match. You're not testing the system at that point. You're testing the function. You really want to check your output, so reverse that. I think I just talked way faster than I needed to, trying to keep it short. But that is more or less the end. But if you guys have any questions, I know I talk fast, so